There we go. Okay, so this is homework 2, number 3, timing. So the way this works out, we have a clock at 10 nanoseconds. It changes every 10 nanoseconds. It changes, right? We have a 20 nanosecond period. This is 10. This is 20, and so on and so forth. The other one that we have is this signal that's changing every 12 nanoseconds. Sorry, let me.
Is that homework that we did?
Yes, this is the homework problem, number 2, question 3. Probably been a while, but everybody did it wrong, and I am definitely putting something like this on the exam. So this is a great place to start the review. Okay.
That looks like my homework.
Man, this is really hard when you don't label out all of them. So 10 nanoseconds is here, 12 nanoseconds drops here.
24, 36.
Okay, so
Which is 10, 20, 30, so 6 is here. 48 is going to be 30, 48 is about here.
60.
And then 40, 50, 60 is where it matches. And it continues on. This is 70, so we're going to get 72. Okay. And we're going to have, now we're going to look at Q, right? So Q, we're going to say starts high, is what the homework problem says. We know nothing can happen until it's rising edge, right? It's rising edge triggered. But the other thing is that it takes 5 nanoseconds from this trigger to change. So when this happens, we load in this 0. Now the question is, can it load in that 0 reliably? Well, our setup time is 3 nanoseconds. Well, we've got that, right? It's been set up for 3 nanoseconds. And our hold is 2 nanoseconds, which we do have, because this is 10 and this is 12. So we just make timing on this one. So then we go to 0, we plug along, we hit this edge. We're in the same boat where we've been set up for quite a while and we hold for quite a while. So we're still okay, and we're still 0, right? Plugging along at 0. Nothing can change until, well, we know nothing can happen until 5 nanoseconds after this edge trigger. So something could happen here. What does happen here? Well, the edge triggers. Have we set up? No. So now we don't know what we are, at least until 5 nanoseconds after the edge, because that's the next opportunity that you have to load in valid data. So now the question is, do we have 3 nanoseconds beforehand? Yes. And do we have 2 nanoseconds afterwards? Yes, we do, just barely. And we read in a high.
Just did that wrong. I was really close.
Lots of people thought this was X's. And weirdly, lots of you that did this one, for some reason, stopped the X's at the falling edge. This is not right. We can only change on rising edges. And this one does make timing just barely.
So do you provide feedback for our graded homework?
Yes.
Yeah.
I've been pretty decent about the feedback. If you need further clarification, go ahead and ask. So like if I give you guys a state machine diagram on the feedback, and you drew something like S0 to S1, and you had something, and you had an arrow here and an arrow here, and this was wrong, I would take my red marker and put a line through the one that's wrong. Or if you needed an extra one, I would draw it in and label it as, right, however you needed it to be. So I do try and fill it in. The more wrong you are, the harder it is for me to notate.
Can we go over the path?
Which one?
Can we go over this path where it's like the
Yes.
because that's not how I was taught.
That's fine. when I started grading, I was marking wrong for some of the weird notation I was seeing. I went back and changed it. If I've marked you wrong for weird notation, write me and send me a message, probably after the exam, and I will fix that. I've already had one student do so. It's fine. I don't like, there's two different ways to do it, and I don't like one of them because I like explicit callouts. Let's see if I might be designing a state machine in one of these. We'll get to it now. But so the general idea is if I have a state machine and I'm in a more state machine, right? That means my output is dependent on my state. So I would do that for my output, right? And if I had two outputs, I would put that as like 0, 1. Rather than defining, so the other way to do it is you say like Y5 is something, and then you would write, and so I'd have Y5 and Y6, right? And then here you would just, you're only writing it if it's asserted, or you're doing the bar. I don't like that, because if your handwriting is bad, I have no idea what's going on.
Right.
If your handwriting is bad, I can still tell the difference between a 0 and a 1. Similarly, for a more state machine, it happens on the transitions. So this is a 1. A 1 happened and my output is 0, 1, say. Do this. I much prefer it to the Y5 example, right? So say that Y5 was asserted on this transition. I still prefer the 0, 1. It is still helpful to say something like this, right? Just to visually identify which one is Y5 for you and which one is Y6. I don't need the whole truth table, but just saying this is enough.
I don't think we did either of those.
That's, yeah, there are.
You did a path for 1 and a path for 0.
Yeah, well, that would be this as well, right?
Right. But we just never were explicit about.
We didn't do very many annealing machines.
That's true.
Okay. This is the way I like it and prefer it.
Sure.
It's the safest way to ensure that you get the right grade. Let's just say it that way.
Sure. I'm fine with doing it that way. I just needed to learn the convention.
Yeah, okay. But if I mark you down for something other, just send me a message and I'll try and fix it. As long as it's clear what the answer is. Sometimes it's just not. I've seen some really weird notations. Okay. The next problem that 80+% of you missed was homework 2, question 4, where you're using the same flip-flop that we just talked about. So it still has the 3 nanosecond setup and the 2 nanosecond hold requirement, and the 5 nanosecond clock to Q, right? So then the question is, what is the minimum or maximum delay that you can have through combinational circuitry in, I think, a state machine, right? So it says something like, say we've used this to implement a state machine, what is the maximum? So as we talked about a little bit, the general look for this is we're going to have some block of combinational logic. That's going to feed into a flip-flop. Right? This is basically all it is. This is holding our current state, and this is holding our next state. So the question is, if this changes, what is the maximum delay I can have for this to happen, assuming a 20 nanosecond clock period, right?
What time that you don't have for setup and hold?
Not quite. So that's the assumption. But everybody that did it didn't take into account this 20 nanoseconds.
So take a time and then say minus out your setup and hold
Yes,
time from.
yes, exactly. We need to minus out things, not just add things up. So most people just they did something like clock to queue plus hold plus setup or something like that. That is not correct. That is 80% of people. But let's think about this, right? So I'm coming along and I clock something in. There's going to be some clock to queue delay, right? That's 5. Then there's going to be some required setup time, right? Before I can clock this in. So before I can have my next clock, I need to have my period minus whatever my clock to queue is, minus however much time I need to set it up. Does hold time matter? No, clock to queue is different than hold. Clock to queue is the time that it takes between this clock happening and it taking D to Q.
Also, it's the actual propagation of the case.
Yes.
Would the whole time matter if it was greater than the clock?
Well, the whole time could matter if it was ridiculous. But as long as the whole time is approximately the same as the setup time, there's going to be no issues, right? And what this shows is that I can have crazy delays as long as my period is large. And this is what people are missing, is that this equation assumes that it's the same regardless of what my clock speed is. And that doesn't make sense, right? So what does the hold time limit? It's actually kind of an interesting question. The hold time matters, and it really might be a problem.
I feel like the limit is the clock.
Hmm?
I feel like the limit is the clock.
Well,
I guess
kind of.
The clock to Q because
but see, the thing is, the clock doesn't care. The clock can do this just fine. As long as the circuit has enough time to register that there was a positive edge. I don't need a 50-50 distributed clock. The clock doesn't determine the hold time by any means, unless you're using a clock as like an enable or something, which you could do, but don't. So generally in the timing for combinational circuitry, hold time doesn't matter. Hold time does matter for other ways, but not in the propagation delay of a state machine. Because you don't want to change, right? The hold time is saying don't change it too soon. So you could imagine a situation, maybe not in this one, I haven't thought it out enough because it just popped in my head, in which the delay through the combinational is actually too small. Right? And then the hold time would matter. So you may need to be in a situation where your combinational logic has at least X delay, and then you would look at the hold time.
so it would still register your clock rising. And then even though the clock is no longer in that same clock cycle, no matter what the propagation delay is, it's still going to register. Right?
Yes, as long as we're still in the same clock cycle. Yeah, as long as the propagation delay, which if you're defining propagation delay as the clock to Q plus the setup time,
yeah,
which is not quite accurate, but if that's your definition of it, then yes, as long as that time does not exceed relative to your clock speed, then you're okay.
So it's just as long as it hasn't gone to another rising edge.
Yeah.
There, okay.
Yes. Chapter 1.8. What page is that on? 43. how do you guys feel about, because there will be a question on this, the finding the hazards, right? So the glitches.
I think we should go over that.
You want to go over that? Okay. If everybody in here says something that's like, oh, that's so easy and boring, then I will skip over it. But
Is it outside of just K mapping? Like, is there another way to do it other than looking at a K map and seeing potential?
well, so that's the thing. The K-map will tell you potential, but it doesn't necessarily mean it's there.
Gotcha.
But I could do something like this, where I'm going to take this. And I don't have the answer to this one, but I can help with the thought process. If there's a mistake, I apologize. Because I'm sure someone will point it out to me eventually. Because they'll be like, you did this wrong.
Just say it was a glitch.
Okay, so this is going to be okay.
Which question is this?
1.8, page 43. Okay. Is it really warm in here today, or is it just me?
It feels really nice right now.
I'm dying of
Not, do not.
Hmm?
What's the second?
This? Sorry, this is A naught, B naught,
It is a B, okay.
A. So we have 4 inputs. And the question is, find all of the static hazards, right? So a static hazard is where you're supposed to be staying at a 1 and you don't for some amount of time, or you're supposed to be staying at a 0 and you don't, right? So if you're just given the circuit, we don't have the K-map. I mean, you could make the K-map pretty easily, but let's say we don't have the K-map. And I just look at this. Where am I going to potentially experience hazards? Yeah, exactly. So A has a different number of gates in the path. B, though, well, it might be, except for the fact that it has the same number of gates and they're the same gates. D isn't anywhere else. So A is really our only culprit in this one. Right? It would be different if we had to take B and had an inverter here.
So this isn't the same one that we had on the homework, right?
No, this is not the same one.
Because I was like, wait a minute. Because the homework, I'm pretty sure it was C that was.
Yeah, so I'm giving you a different one.
Okay, all right.
A different example, new material. I just wanted to go over the other homework ones because it was useful. So now we have 2 possibilities that it could either be when A is going from 0 to 1 or from 1 to 0. You don't necessarily have to be able to tell that, but what you want to do then is make sure that everything else is set up in such a way that the gates are going to respond when A changes. Right? So this AND gate, if we don't have this happening, if this isn't true, this A changing will never even be seen here, right? So we know that this first gate has to be true. So if I have, I should have done it all capital letters, but D, C, B, A. Let's go ahead and look at B and C. So we need B or C bar. Oh, did I?
Yeah, it's B not.
It is B naught. Okay. All right. So, or, well, we can do either one of those. So let's just say B is 0, right? So that way we're good. A or B, this is good because if B was 1, this A wouldn't matter, right? So here we're seeing that we need B to be 0 for this OR gate to ever react to this A. Because if B is 1, this is just going to stick at 1, and there's no chance of a glitch.
Right now is finding where the glitch happens, right?
Yeah, so we're trying to figure out, well, we know the glitch is going to happen with A, but we want to set the circuit up in such a way that when A changes, we will actually catch the glitch.
Right.
If B is 1, we will never catch the glitch.
Right.
They're
just isolating A.
Similarly, D is D bar. It's ANDed with this A bar. So if this path is not true, the output of this gate will never react. So we need this to be true, so D also has to be 0. Right? Any other one? C doesn't really matter what that is. So why not? We're going to go 0. Now we have to decide, do we want to go from 0 to 1 or from 1 to 0, right? I don't know a quick way to assess the right one to look at. Fortunately, once you've identified the right pattern, it's not too difficult. So let's say we go from a 0 to a 1. And let's just assume that all gates have 1 nanosecond delays. So A is a 0. So that means this path is a 1. This path is a 1. And this is 1. Just to follow through, A is a 0, B is a 0, so this is 0, which means this is 0, right? We know this is 1, because we set it that way.
Isn't A 1 in that case?
A, we're 0. We're starting at 0. We're going to go from 0 to 1.
It's not A naught.
So this is just A.
Yeah. I thought we were at 1 already, sorry.
No, yeah. So I'm starting out where we are. So we're 1 because this path is 1. Okay, now we're going to change to 0. And we know that this path is going to become false and this path is going to become true. So then we just find the difference in those delays. And
1 nanosecond.
yeah, I mean, you can just assume 1 nanosecond or 5, whatever it is. 1 is just easy number to deal with, right? Unless the book or my question assigns some value, because you could do something like this has 5 and this has 3 nanoseconds of delay, but that's more complicated than we're going to worry about right now for the example. So now we could probably start thinking our way through, is this going to cause us a problem? Because we're going from 0 to 1, and this is 1 and will become false, and this will become true. If this one becomes true before this becomes false, there's no issue, right? Because the output is ORed, so that the overlap is going to be good. This is a slower path. So this one is going to become 0, and then this one is going to become 1. So we found our real potential for hazard.
So there's going to be a false, so we go 1 and then we switch. It's going to be 0 for 1 nanosecond, and then it's going to go back up to 1.
Yes, exactly. And so this is, I'm trying to explain kind of the intuition on this, right? It's a race between this path and this path. And we want one of them to win. We would prefer this one to win, but it's not going to. Right? So then we can go through the timing of this, the actual draw. So you would have, let's call this node X. No, let's do this X, Y, and Z on the timing. So X is 0, becomes 1. 1 nanosecond after that, this is 1 nanosecond, Y becomes, sorry. So this is at so this is 0 nanoseconds, which is when A changes. So A changes at time 0. 1 nanosecond later, X changes. 1 nanosecond, Y changes. And 1 nanosecond later, Z changes. Then, shoot, I should have done this over here because now we're going to have a little bit of an issue. But we can see that Z changes at 1, 2, 3 nanoseconds. And Y changes at 2. Similarly, we can call this node alpha. So at time 0, we have node alpha and Z. And 1 nanosecond after A changes, alpha drops to 0. And 1 nanosecond after that, Z drops to 0. So Z is dropping to 0 at 2 nanoseconds, and this is dropping at 1 nanosecond. And then if you stack those up, you can see that this is 0, and at the same time, this Z is 0. So your output is 0. So your final output of Z is going to look like this. So that's kind of how I would do it. Is if I get the circuit up there, I can kind of look and see which one we would hope would be faster.
So a 0 to 1 would cause this.
Causes this.
So 1 to 0 wouldn't cause this.
No errors.
Because it's a 1, 1 on your OR date. So in that case, it's still correct, but kind of for the wrong reason.
Yes. Well, so here this would be a static 1 hazard, right?
Yeah.
Because it's supposed to stay 1 this whole time, but we don't.
Right.
Yeah.
So with the not A at the top, so are we not assuming there's like an inverter that's another delay?
No, because sometimes so we're just assuming this is our circuit. If I'm in a question, I say you have inputs A, B, and C, then you would have to go back and start drawing your inverters, right? And you can start fixing hazards by throwing inverters, like an invert and invert, and you fixed it, right? The other one that can start fixing it is you go back to the K-map and make sure. So this is also a question that people missed a little bit of.
So will you always have a static 1 or a static 0, or is there ways to like get rid of both?
There's ways to get rid of both.
Besides using the buffers or the
Yeah,
inverters?
so the way to do it is you come back to the K-map, say this is my K-map. If I did the obvious one, I'm probably going to have a hazard.
Okay.
Almost certainly going to have a hazard. However, I can add a third term,
To prevent that.
and now I no longer have a potential for a hazard. Adding the third term doesn't change the output, but it does add an extra gate. And then what that extra gate will do is it will enter the race and make sure that it counteracts any problems going on from any other race conditions that arise.
So it just kind of makes the number of gates equal, so that you have your own.
It creates a third path, which will have an extra, the correct delay.
Your delay is match.
And this won't always cause a hazard. If you end up with no inverted signals from your K-map, so you end up with only if your only terms are A, B, and C, which is a really trivial solution, you won't have a race condition. Or if all of your terms have both knots and inverted and not inverted. I'm not sure if that's true. We could go back and prove it, but the adjacent without sharing an implicant, right, which is the circle means, is there's a serious probability of a hazard existing.
not conceptually.
Okay, the next one. 245 on page 132. Okay, I'm not going to write this up. This will take too much time. I'm going to assume that you guys don't all have your books handy. So what I'm going to do, oh man.
Which problem are you doing? Which problem are you doing?
245. I can make the stupid projector and the recorder work at the same time, but to do it, I have to be recording on my laptop, and I'm not. So let me do a pseudo code of this. So it's asking for some VHDL. You know, forgive me if I don't write everything perfectly correct. This question is so trivial, but I want to use an example.
Was this the one on our homework?
No.
This is the one on our homework.
So if I give you this and ask, what is it? VHDL code. What device is this implementing?
Asynchronous T flip-flop,
Yes, an asynchronous T flip-flop.
an active high reset.
Yes. So those are going to be some of the questions. Is I might show you VHDL, and it'll be for some common device, and then I will ask you, what is this doing? Yeah.
We have something like I think it was homework 3 that has a whole shift register thing. Is there anything going to be that complex? Where it was like you could go 4 different ways with that.
It could be. Because hopefully you're smarter now than during homework 3. Other things that I might do, so pretend that I provide actually good code rather than this kind of hodgepodge pseudocode, right? This is somewhere between real code and like pseudocode. But I could also do something like this and ask, is this reset synchronous or asynchronous?
It's asynchronous.
Synchronous.
Synchronous has a block.
Because if it's not in my sensitivity list, I could assert reset and not reset, as long as I didn't do it during the rising edge of the clock. Right? So if I had clock here, so this is clock, and this is reset. I didn't reset, did I?
No.
If I have reset up here, then I would. So I could do that. So I could also provide code for you and be like, make this into add a synchronous or an asynchronous reset.
Wouldn't that basically be able to reset on the falling edge and the rising edge? Because there's no dipstick for the rising edge.
Yes, it could. So I can and will do things like that, where I will ask you questions and I will give you minor problems in them and then ask you to point them out, right? If I'm feeling particularly mean, I might like write the code out correctly and not do that.
Oh my gosh,
Oh, that's evil.
that is just straight up.
But we don't know the.
I would make sure to give you the types.
Okay, I was gonna say that we get an answer.
Yeah, no, yeah, if that's the case, you don't know.
Right.
But if I give it to you, I will have synthesizable tested logic that is there, so there's not an error. Yeah.
So to clarify, could we go over like the types and what you use? Because I know that like integer, you don't use any quotation marks or marks at all.
Yes.
Yeah,
So the big three that you should know
integer
is
vector
the standard logic is apostrophes. The standard logic, I'm just going to write vector, V for vector, is quotes. And an integer is nothing. Those are your big three. You're going to possibly run into some issues where I might ask something along the lines of, and this is where having decent notes, like I recommend, so I'm gonna have open notes, open book. I still recommend taking like one sheet of paper and putting your most important notes there so that you spend way less time flipping through. And right, we call the IEEE library for the to be able to use the standard logic rather than just a bit vector. And there are operations that you can do on standard logic vectors that you can't do on a logic vector. So if you don't have the IEEE, and I might ask something like that. Is this a viable operation, and try and add two things together that can't add together?
So like if you're trying to add a standard.
Trying to add a
You're in a standard logic vector.
Yeah, and just logic vectors, is that what they call them? I have to make sure.
They don't really do much with anything else, do they?
No, they don't, because everybody in the world imports this library, which is the IEEE standard logic library, right?
We're not gonna have anything to do with for loops on this, are we?
Why not?
I'm trying so hard to get this for loop to work, but I can't get crap on it. And I'm not the only one. There's a couple other people like in the day class that can't get the for loop to work.
So things about the for loops, it has to be in a process, right?
Right, got that.
So it doesn't make sense to not be in a process. The other one is, Jace used to be the expert on this, right?
Yeah.
Yeah, she worked on this for hours.
So JC will correct me if I'm wrong as I do this. Is a for loop is nothing more than saying for your iteration variable. I always use double I's or I, K, K, J, J.
Right. Good coding for that. For
I know it ends up with like 0, like in,
Yep, so
0
for I
to
in 0 to
n,
loop.
yeah, and then you say loop.
Right, okay.
And then if you wanted to start iterating through something, the syntax is did you try the syntax that I showed you?
So it wouldn't let me run a synthesis, but it didn't have errors, like it didn't have red lines.
Okay, so you can look at my test bench to make sure this is true because the for loop there works, right? But it is something like, if I wanted to go through what the homework is looking for ones in some vector x, you could do something like if x at I is equal to 1, do stuff.
What about then?
Well, It's just pseudocode. Yes, there's if this, then that, right? I am not going to mark you down for most of these. Most of the questions, if I have you write code and you miss a begin and a then, I don't really care. I may do something like, say something, the way I might say it, and I'll probably do this, is be like, attempt to write good code, I will forgive 5 minor syntax errors, right?
Oh, no.
So you'll have to give a good effort to it, but it'll be fairly forgiving. So it's like, I forgot 3 semicolons and 1 begin end, right?
That's gonna kill me.
I know, but it'll be fairly forgiving.
Okay, let me read you this code and you tell me like, so I got for I in that, so I got for I in 0 to 3 loop, right?
Yeah.
Then I got if x, or I, the same variable, is equal to 1, then I do counter is, or assert counter to counter plus 1, and then end it and then end loop. That should work, right?
So
And counter is of type integer.
yes.
That should work.
My only concern here is that this is an element in a standard logic vector.
Also, by the way, counter is asserted to 0 before the for loop.
Yeah. So as long as you've initialized it to 0. So you come in here, C is 0. I'm not 100% sure because I haven't dealt with this yet. If the an element of a bit vector is equal to a bit,
It's not throwing an error.
It works.
it works.
It's not throwing an error.
Use the colon equals to do the.
Oh, this one?
No, on the next line.
Oh.
C,
Yeah.
You have to use the colon there.
I have to use a colon there?
Well, 4,
Because
It's
it's a
not a
type of
signal.
integer.
right? You only use that for signals.
But again, for most part, I'm not going to mark you down for little syntax errors. It's going to be conceptual. I want to know that you know how to write the code. And so you're going to try and write it like code, right? But say that I was like, and this is a bad example, this is a really simple example. Say that I couldn't remember how to do a counter. Then I could just write, then increment counter.
That tells you we know what we.
Then I know what you're trying to do, and you at least get a good chunk of the points from that. So if you know what you're trying to do and you don't know how to do it in VHDL, show me that you know the concept, and you'll still get a good chunk of points.
That's doable.
And now it's throwing me an error to use the error.
Yeah, I'm a little surprised. I almost never use that.
I guess it depends on what you initialize your counter at.
Yes.
If you do it as unsigned,
Um,
then you have to do that.
I don't want to work through this here. This homework isn't due tonight, is it? Oh my gosh, you people. Try and do your homework before that. If we get through the rest of this review, then we'll come back to this problem.
I just thought we were going to go over some of this in class, so I was like, okay, like.
Now, I don't want to go through syntax in class. There's better ways to spend our time.
Is yours working?
I don't have red lines.
Well, mine doesn't have red lines either, but I put in 1, 1, 1, 1 in it, it gives me 1. When it should be 4.
You did it right, Jason.
That's true.
Since apparently multiple people care about this, let me look.
So this is the general idea, but the test bench right here for F, it ends up 1.
Okay, go back to the other one. Show me your test bench.
Okay, but I still need to change the test bench because I just changed the unsigned to integer.
Helps if you spell it right, by the way.
And then I set X in was 1, 1, 1, 1, 1.
Yeah.
Like 500 nanoseconds for whatever reason. And then
Start prepping the
Okay, it's
39.
and then I can as one.
Okay, so what's interesting to me, don't show me B out. Where is that in your code? Okay. So go back to your test bench. Mouse.
Try to put your.
It doesn't change.
So it doesn't change. So that's worrying. Oh,
Go back to its actual code for his thing. I put his assignment to be inside his process.
I tried that as well.
look. Again, it's counter 0.
And so when I did more than one in the test bench, it just incremented like 0, 1, 2, 3, 4, 5, 6. It would only go up until it hit like 7, and then it'd go down to 0. It was like,
Okay. I will have to think about this one for a second. This is why it's good not to wait till the end for homework, is because there could be issues that I can help solve if I have enough time. Okay, so I'm looking at question 2.39. Quite cool. Where we're going to have a more state machine. So I want to make sure that you guys are comfortable looking at something like
Numbers, sorry.
2.39, page 132. I don't know if this is a good example or not yet. We'll find out. So I may, this is a very simple one, give you a state table and ask you to write VHDL to implement this state table. Or it might be a two-parter, I might say, please draw me a state diagram and then write me VHDL. Right? Do you think you could turn this into VHDL?
If I had printed out some VHDL code, yes.
well, it's open computer, right?
Nope.
Oh, not open computer?
It said open note, open book, not open computer.
Okay, so I guess I have to download all my code that I have into my network.
Are you guys gonna make me freaking have to limit the number of note pages you're allowed?
What test was it that Terrence printed like a stack of papers like that?
I've done that plenty of times, dude. I've done that plenty of times.
You guys are insane. Okay.
But I'm doing 3 coding languages at once, like, I need syntax out
So-
of it.
What would we do, right? What's our first step for this VHDL code?
Make the diagram.
Yeah, I was gonna say probably write the diagram.
So let's say we write out the diagram. I don't want to do every bit of this, but I do want to walk through the process. So we make the diagram to visualize it and see how it, so we're going to have some circles and some outs. And it's a more state machine, so it's going to be like S1 is 0 and S2 is 1, right? And there's some paths between these. And this is kind of like annoying logic because there's only 2 states. But then we're going to need to do something. What does our main structure look like for this? Yes, case. And we're going to do some case on state. I will try and say things like you don't need to declare your variables if you don't need to, right? Because I can generally assume what you are. What is the requirement? Can a case statement just go anywhere, or does it have to go somewhere specific? It needs to be inside of a process, right? And then our process is certainly going to be on a clock.
Not the state.
Well, not really, right? If we're in a melee machine, maybe want to change on state, but probably not. Probably more, we only want to update on the clock, and maybe a reset if we're going to design for that. In which case, we would need to also, what's our issue right now that we have even if we don't do reset? Let's say we only case on clock. What's our issue? Well, just where we've gotten so far.
If you can't reset, when you just get stuck in a state and then you're.
Okay, so let's say there's no worry about reset, there's no worry about getting stuck. We want to update the state on each clock. Are we currently updating on once a clock?
No, don't we need to do it.
Why not, JC?
We're not calling the rising edge.
Yes, exactly. We're not calling out if rising edge, so we're updating twice per clock, right? Good catch. So we would want to add an if rising edge. Then we're going to go into the case, right? And now we can, once we're inside the case, now we can start doing when, right? We're in 0, 0, right? And this is a logic vector, so we probably want to do that. Then we do this arrow, I think.
Yeah.
Again, a little bit forgiving. If you write then there, I'm not going to be like, ah! Then we're going to write the logic for this, and then we're going to write the logic for state 2. There's only 2 states. I don't think I need to write that out. It's just in these cases, right, we have 2 inputs.
If you were to say include a reset, could you include the reset as a state?
That would be not exactly, because you would have to have a bit reset and a enumerated type reset, right? The states and the bit are different things.
State itself would be a different.
Yeah, so you could create a state called reset if you needed to go into it for a beat, right? So like I want to go into reset, take a breather, I'm going to assert some signal on my output, say I have reset, and now I'm going to set back to idle and be ready to go, right? And you might see other things. I actually have a question that I may throw in there that's kind of interesting, where you go into the first state when you start up, but as soon as you start getting data, you never return to the first state, right? And we see that all the time, actually, in initialization states.
Yeah.
Other thing in states to be aware of, right? If I have a counter inside here, if I don't know what C is coming in, I can't add to it, right? So make sure that you assign C to something.
Does that need to be like there or plus or above? Because you could just say C goes to 0 and then C.
Yeah, so you could inside, I mean, I would build it into, it depends what you're doing, right? So in our lap 1, I built that into our reset state. And so anytime you go back to reset, it resets all of the counters. And then if I need to initialize it to a non-zero number, I always do it on the next state logic. So I say, so if something, I say in present state, else something, I'm going to next state, and counters getting asserted to 7 because I have 7 bits to count down to the next one. So this C equals 7 gets used in the next when, right? So I like to initialize it here,
Yeah.
and then use it in the next state.
And basically there you just have to be
do it either way, but you have to be consistent when you do it.
Yeah, and you have to be very careful because it's very difficult to write code that initializes a C when you enter a state.
Right.
It's
You don't-
sometimes possible, but it's not worth the effort. It's much easier to initialize it when you leave a state. Because otherwise, if I just set C equal to 7 here as the initialization, every time I enter that when, it's just going to reset to 7, and now it's 7, and now it's 7. It'll never do anything else.
Right.
The one exception I can think of is if you know it's not going to be 7 here, you can go set C equal to 7, but you would have that inside an if C isn't 7, set it to 7, and now start counting down from there. So it goes to 7 and then immediately gets decremented, and then you have an issue, so you have to raise a flag that says and not flag, and then you raise the flag to not go back into that. So you have if isn't 7 and not flag, right? So it starts getting a mess when you could just do this.
Yeah.
Keep that in mind. There'll probably be something, because anything is fair game if it's from a homework, reading, or lab. I will definitely ask something about the lab because it's an important part of this class.
Don't be nice with that, because that can get tricky.
No, you're all experts on UARTs now.
Oh, yeah.
I may do something just to make sure that you didn't just completely zone out to chapter 3. I may make you do some diagram. I will provide this diagram for you.
We should have to draw the little dots and connect them.
And then ask you to implement some function in this. Right, and I could switch these around a little bit. I could change these gates to like XORs or something, and you'd have to do some gate transformation. I wouldn't do that to XORs because that's just me, but
Yeah.
right. I might turn this into NANDs, for example. Like this is an AND, and that's an AND. And then you'd be like, I need not, so this would be B, and this is A. So I need not B and A, right? So the output here is A and not B. That's what this means, right? And then if I have these wires, then this could be, say, I mean, this is probably trivial logic, right? Because this is just an XOR. Or maybe it's an, anyways, it's something that's probably fairly trivial. But then I could say this and, oh wait, I wouldn't have a second wire, right? Single wire, this is now this or this is output here. Right, so that's just that diagram. That way, if anybody completely zoned out and then doesn't watch the review, they get screwed over. But if anybody that paid any attention is going to be like, okay, this is dumb.
Yeah, that's right.
Why did I not print that out? Do you have homework 2 number 1 pulled up?
Homework 2, number 1.
Was the meeting
Yeah.
live from the
42,
yeah,
No, I deleted it. Like, I can get it really fast though. So just to be clear, like on notes and stuff, like what are you about? Like, only printed paper?
Printed paper. I don't want digital things out.
Well,
and I kind of wrong.
I could make it so you get 1 sheet of papers like I had when I had this exam.
Thanks a lot, Jason.
You get one sheet. Yeah, you should see the exam. I pulled out my exam for this exam. You guys would hate it.
If you give us one sheet, then we will probably,
What if that,
we'll do a blue font for one and a red font for another, and then we'll wear 3D glasses.
that'd be kind of cool.
So you can overlap it, but when you wear the glasses, you can separate.
So while we're waiting, I will show you the worst thing that I can do on this exam. It is based off of one of the homeworks. This might be the one I have been pulling up, actually. That would say something like,
There you go. Wait, homework 3.1? Or
2.1.
Okay, one.
Homework 2, number 1. I just don't remember what it is.
There was an S and Y5 and Y6.
Yeah. Yeah, so this is what this is.
Well, it's in a Word document.
Something like that. So that's what you've done, right? You've done this thing that detect 110 or 101.
Yeah.
I could, based on what you guys currently know, whether you guys reckon or not, this would be the full extent of the question.
But you can make it way confusing.
Well, no, this would be the question. Design a circuit to detect 110 or 101. How do we do this? Okay, so we doodle out the state machine. We get it from homework 2, right? And that's the number 1. That's the one that we designed. I don't have it with me, which is really unfortunate. Oh wait, maybe I do.
What do you need?
So you have to almost like make like 2 paths for that one. Like, is it both of those? Like this one or 1?
Yeah, because that's what homework 2 is, right? Number 1. Where Y5 is this.
Yeah, that one was kind of hard. I mean, I think I got it right because you didn't mark it down, but.
Right? So Y5 or Y6, and you end up with and it tells you something like you can do this in 4 states. It gives you a hint.
I actually like this one. This one was kind of fun. I got classes with I haven't seen the either. Oh, yeah. He was going through this. He was not
I can't remember my stages of desperation for debugging. You know? Like number 1, syntax.
Yeah.
Number 2, variables. Number 3, case statements. Number 4, put everything.
Okay.
Keep the sense of the.
So here's our state machine to detect that. Right? But that's still not a circuit, is it? I have a state machine, but I have a circuit. Question is, design a circuit to detect this.
Oh, shoot. You gotta do all the flip flops.
Yeah. We know how those look, right?
If I had the book, yes.
How many flip-flops do I need for this state machine?
3,
4.
4.
2. What are you guys doing to me? 2. You guys are making me dumb. Come on. A, B, 0, 0, 0, 1, 1, 0, 1, 1. 2 flip-flops. Right? Because what do my flip-flops store? They store my state. I only have 4 states. 2 to the n, we're good?
2 to the end.
Okay. Okay, so now we have that. Now we can start drawing up something like either a state table, which this is basically the same thing, right? But we also know that we have flip-flops.
So we have to draw up the table and then go.
Okay, so these don't change. I have a Q0, Q1, don't need that.
Yeah, for a second I was like, wait, didn't you just call me dumb for
And here I have combinational logic, right? My inputs to this combinational logic then are
Q0, Q1,
and
reset. No, reset doesn't go to clock, does it?
well, let's just put it at the bottom like everything else is. X, right? That streams in. Okay, so we're a little bit closer. How do we just start designing the combinational circuits?
You gotta make the state, or like you gotta draw them out. Like you gotta take that and turn into a logic diagram.
Yes, we need to make our decisions into some form of logic. So a couple ways to do this is if it's nice and simple, your inputs to the logic, right? X, Q0, and Q1. Those are our inputs. Right?
Right.
And we know that if we have a state where our X is, let's just jump to an interesting one, 0. Our state is D. So we've assigned, we'll assign it this way, A, B, C, D. Then our Z for, which is this, Y6. Well, rather than call it ZY6, let's just call it Y6, is 1, right? Because my X is 0, I'm in this state, I want Y6. Then I have another column for Y5, and I can build out this truth table, right? And then once I've done that, I can use what tool to build a circuit? K-map. Yeah, we'll go K-map, simplify it, build out the combinational circuitry. Yeah.
Is it, so say you do put that on the exam, is that just gonna be one problem?
Worth a lot of points.
Okay.
Yes, one copy.
I mean, I could do multiple parts, right? I would do this, and part A is draw me a state diagram. And then part B is,
Well, sorry, let me rephrase my question. Say I understand the back half, but say I get stuck in the beginning, am I screwed?
no. I will try and give you points to through. This is why I'm not 100% sure I'll do this unless I can find a way to break it up. Because I don't necessarily like that.
Just give a K.
But the question that I got on this exam is, it literally says, design a circuit to detect the sequence 10110. That was it. That was the whole question. That's that. And what you want to end up with is this. Right? So there's various ways that I might ask this. So my point is that you know how to do this. You might not recognize that you know how to do this, but you do know how to do this. But I might start out and say, giving you the state table and ask this. I might give you all the way up until this diagram and then ask you to give me the combinational circuitry. Right? There's a bunch of things, the ways that I can ask this. But be aware that this is a question that should be in your head. I won't do what the book does in some of these questions and do this with 7 variables, where you have to start doing math-centered variables to start solving this. I won't do that.
Are there gonna be map-centered variables on the test?
I will not do more than 6 variables in a K-map.
Okay, so we could do
So
it the way-
MEV is optional to know. You can use MEVs for 6 variables or not.
or we could do it the way that we
Yeah.
did it with you.
Yeah, the cube version. Your choice. Those were the things that I had listed that I really wanted to cover, because that's what I was noticing people struggling on. If there are other questions or things that we want to go through, we've got probably 40 minutes. Well, yeah, 40 minutes.
With the combinational logic right there, like the actual just drawing out the AND gates, or are you talking about
Yep.
the actual code version?
No, it'll be AND gates.
AND gates.
Yeah, so if I say design a circuit, I do mean AND gates. If I want code, I'll ask for VHDL. As I said, I will design it for 1 hour. I'm new to test designing. I will try and make it. My strong recommendation, I'll remind you on test day, is to do what you know how to do. Feel confident in it, get those answers, and then come back to anything that's confusing to you. Because if it's really hard for any of you individually, it's probably really hard for everyone, and I will curve it down. I do not want to have the high score be a C. That's just not cool. So I want to design it where the high score is like 99, right? And I get a nice bell curve around that. That would be my ideal, but I'm new to this test designing thing. Yeah.
So you said something about the possibility of taking it online. I'm just wondering because a lot of us have another exam that day, so I'm wondering if it's better for me to be home and try and do it online, or if
so, I don't want too many people to do it online. Most people show up. So if it's online, I'm pulling up. They're going to have to log into Zoom and then take it while I proctor it at the same time. It's not like you'll be able to do it at your own time.
Right. And I figure as much. It like takes time out of the day to like come to campus
the commute.
and go back. So I was wondering,
What time is your other exam?
It's the entire day.
It's the entire day.
Yeah. But I'm also in class the entire day.
Yeah, hypothetical
Are you in class 9
is
or
a
9 a.m.
Thursday
Yeah.
Do we have a lab
option
next week for 3210?
possible
Is a Thursday.
exam. Just because I know that there's a bunch of people in your morning class that are also in this signals and systems class.
Interesting. But the signal, their signals and systems is also going to be, what day is this exam? Tuesday?
So the day section is Monday for the signal.
Oh, it is?
Well, there's two. There's one Monday for whoever had a Monday, one Tuesday for whoever had a Tuesday. So.
Okay. Let me stop this recording. I don't think that.
Okay, yeah, they want to hear. There's four of us in this class right now have to take it that Tuesday next Tuesday.